Okay, evening. Can you hear me?
Yes.
Yeah. So we will assume week 10, the last bit for week 10. Okay. So what we have so far seen is we have looked at this whole idea of duality and duality gap for general problems, right? So that is what we have seen. We have also looked at what is called as strong duality, weak duality, all these things. Yeah. Yes. You have doubt?
Yeah, so I just wanted to clarify whether you're recording this particular session and where I can access the recording for future reference when I'm preparing.
The playlist is there, right? The course playlist. We have a live session playlist.
In the YouTube channel itself.
No, there is a separate playlist for the course, right? Live sessions.
Okay, where can I find the where can I find the link to the playlist?
You have to search in this particular channel.
Okay. All right. Thank you.
Okay. So yeah, so that is what we have seen so far. So what we will do today is, instead of looking at any general constraint optimization problem, we will specifically look at convex optimization problems, right? So the first thing that we will do is we will define what is a convex optimization problem. So we will take things one at a time. So there's a very simple setup that we will look at first. So consider an optimization problem. Consider a constraint of the form, the usual form, right? So you want to minimize f of x subject to some g of x less than or equal to 0, right? So that's the usual form. So this is called a convex optimization problem if f and g are convex. Okay, so if you have a single inequality constraint and if you have the objective function which is of the form f of x, right? So then this is called a convex optimization problem if both the functions are convex, right? So mainly the objective is convex, the inequality constraint should be convex. Okay, now there are slightly more complex problems that you could think of in general, right? So if you have a constraint optimization problem of this form, where you have minimize f of x, that remains the same, but then you have multiple constraints. So maybe you have g1 of x. So whenever I say x is in rd or rn. Okay, so with the optimization variable being n dimensional. Okay, so you could have g1 less than or equal to g1 of x less than or equal to 0, so on and so forth. Okay, till g, let's say n, or we have used n, so maybe in fact let's use what gm. Okay, so gm of x less than or equal to 0, you have m inequality constraints, and then you have say some k equality constraints. So for a convex optimization problem, these equality constraints have to be linear. Okay, so what we can do is we can represent it as some ax equal to b. Okay, so this is what is called a convex optimization problem in general. Okay, so the above problem is a convex optimization problem provided following whole, right? So f is convex, the objective function obviously has to be convex, gi, right? All the inequality constraints are convex and all the equality constraints are affine. Okay, so the term for this is affine. So if you look at each equality constraint, it will be something of the form a1x1 plus a2x2 plus dot 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 plus a n x n equal to say some b. Okay, so this will be one of the equality constraints. Okay, so this is a convex optimization problem in general, but for this session what we'll do is we'll concern ourselves with only this form where you have a convex objective function and convex inequality constraint. Okay, is this clear to everyone what we mean by a convex optimization problem? Okay, I hope it's clear to all of you. So once that is clear, we'll go ahead and look at what are called the KKT conditions corresponding to convex optimization problem. So why are we studying convex optimization problems? The reason is they are very popular in machine learning. So you have the idea of a loss function in ML, right? So you have all seen what a loss function is. So can someone tell me some loss functions that you know that you have come across so far in machine learning?
So like a mean squared error.
Yeah, the mean squared error. Okay, so mean squared error is one such loss function. This is convex. Anything else that you have come across? Okay, I think we have only, yeah, anyone?
Negative log likelihood.
Yeah, negative log likelihood, that's good. So that is also a convex loss function. Okay, so why is that convex? So negative log is convex. Now, depending on, so for certain situations, the negative log likelihood is indeed convex. So whatever you put inside the log, if it is convex, negative log is anyway convex. So, and negative log is not just convex, it is also anyway, so that we'll come back to that later. So I'll give you a few more examples. So there are what are called convex surrogates, which you will study in week 12 in MLT, right? So those who are doing MLT, MLF together might come across this, but if not, there is a special week devoted to what are called convex surrogate loss functions, and you will see why convex functions are so important right at the end of the next course. But until then, you have to trust whatever we are saying when we say that convex optimization problems are widely used in ML. Okay, so that is a brief motivation for what we are going to do today. So let's once again state this problem. We are trying to minimize f of x. So consider f and g to be convex, okay, functions. Now minimize f subject to g of x less than or equal to 0. Okay, so we are now going to look at what are called the KKT conditions. So let us now state the KKT conditions. Okay, at some point x star and lambda star. Okay, so before you state the KKT conditions, what are the two setups that you need? You have one optimization problem. What is the other thing that you need if you want to state the KKT conditions? We need to have the primal and the dual problem, right? So unless you set up the primal and the dual, you really don't have you can't start talking properly about KKT conditions. So consider f and g to be convex functions. Then we have the primal problem given below, right? So this is the primal problem. So let us also state the dual problem. So what is the dual problem? Does anyone remember what the dual problem is?
So lambda should be all positive.
Okay.
Maximize over lambda, minimize over x.
Yeah, maximize over lambda greater than or equal to 0, minimize over x. What do you minimize? The Lagrangian, right? So f of x plus lambda g of x. Okay, so so this is the primal. So you have the primal problem here. Let us, in fact, before going to the dual, we can state the equivalent form of the primal problem. So that is what? That is min over
X.
Max.
Max over lambda Lagrangian.
Yeah, max over lambda greater than or equal to 0, Lagrangian once again, right? So f of x plus lambda g of x. So whenever lambda is greater than or equal to 0, and whenever the constraint is satisfied, this will fall back to f of x itself, right? This whole thing will become f of x. Whenever the constraint is satisfied, if this will become f of x, and this is just minimize f of x, g of x less than or equal to 0. Okay, so now swapping the max and min, we have the dual problem. Okay, so that is the setup that you have to always keep in mind. Okay, so this is the primal, this is the dual. Now let us now state the KKT conditions at some point x star comma lambda star. Okay, so there are four conditions, right? So let's call this one. So what is the first condition?
Sir,
The
stationary.
derivative of Lagrangian should be 0.
Yeah, the derivative of the Lagrangian should be 0, right? So this is called the stationarity of the Lagrangian. So the gradient with respect to x of f of x plus lambda g of x, right? So this at x star, okay, and lambda star. So that is, those are the points where we are actually looking at the KKT conditions. Okay, so this has to be 0. So let me make it aligned. Yeah, this is okay. Okay, this has to be 0. So this is the first condition. This is called the stationarity of the Lagrangian. Okay, so stationary point is nothing but a point where the gradient is 0. Okay, so that's where the name stationarity of the Lagrangian comes from. So that is the first condition. Okay, so what is the next condition?
Sir, the main constraint, I mean the prime feasibility.
The primal feasibility, right? So any constraint, sorry, any solution x star to the optimization problem, to the primal problem, has to be feasible, right? So therefore, g of x star has to be less than or equal to 0, right? So this is primal feasibility. Okay, corresponding to this, you have something for the dual, right? What is that?
Lambda greater than equal to 0.
Yeah, lambda star is greater than or equal to 0, right? And this goes by the name of dual feasibility. And finally, what is that do we have?
Complementary slackness.
Yeah, so the lambda star into g of x star has to be 0, right? So this is lambda star into g of x star has to be strictly 0, and this is called
Complementary slackness.
exactly, yeah, so complementary slackness conditions. Okay, so these are your so let's left align this so that everything is on one line. Okay, and maybe add a bit of borders so that they're all nicely separated. Okay, all right. So that is, these are the 4 conditions which are called the KKT conditions. It's at some point x star and x star comma lambda star. Okay, so what we are now going to do is we are going to look at what are called sufficient conditions. Okay, so there are 2 things. There is, we have already seen this right before. There is what is called a sufficient condition, and there's what is called a necessary condition. So the first thing that the first question that we will ask is, if x star and lambda star satisfy the KKT conditions. Okay, so this is the statement of the, so we call this theorem. Okay, so if x, and since it's important, we'll put it inside a box. So what is it stating? If x star and lambda star satisfy the KKT conditions, then x star is the primal optimum and lambda star is the dual optimum. Moreover, f of x star equal to d of lambda star. Okay, so this is what is d? D, by the way, is I haven't defined d, right? So let me define d. So what is d of lambda? Does anyone remember what is d of lambda? We discussed this on Thursday. It is the dual objective function. So whenever we stated the problem, right, I didn't specify what is the objective properly. So maybe I'll quickly state it. So the primal objective is f of x, right? So this is the primal objective. The optimization variable in this case is x, okay? And the primal constraint is g of x, right? Less than or equal to 0. So the primal, this is the primal problem, completely specifying the primal problem. Okay, likewise, you have to specify the same for the dual problem. So for the dual problem, the optimization variable is
Lambda.
lambda. What is the dual objective? We call it d of lambda. This is slightly tricky. It can be a bit confusing. So notice that you are getting rid of x in this problem, right? So you are minimizing over x. Therefore, what remains is some function of lambda. So this whole thing is called the dual objective. So it's d of f of x plus lambda g of x. Okay, this is the dual objective function. It's a function of lambda. Okay, and finally, the dual constraint is very simple in this case. It is lambda non-negative, right? So lambda greater than or equal to 0. Okay, so this is what we have with us now. And what is this theorem telling us? It's telling us something very interesting. So for a convex optimization problem, this is very important, right? So this happens only if f and g are convex. So for a convex optimization problem, if you find two values, x star and lambda star, if you find that they satisfy the KKT conditions, then what we have is that x star is the primal optimum and lambda star is the dual optimum. Not just that, the value of the objective function primal objective is equal to the value of the dual objective at their corresponding optimal points. Okay, so is this clear to everyone what I have written here? Does this make sense what has been written down?
So please explain D once more.
D is the dual objective, right? So what you are doing is, see, this is D. This whatever is there, whatever I highlighted, right? That is D of lambda.
Okay.
Okay, what you are doing is you are minimizing over x. Some function of x and lambda is there. Okay, as far as this inner optimization problem is concerned, lambda doesn't matter. Okay, I'm not that it doesn't matter, but lambda is like a constant as far as this inner optimization is concerned. So it is minimizing over x. But then once you minimize over x, what happens? This becomes just a function of lambda, right? For example, so this could be something like, I'm just making this up, but so this could be lambda greater than or equal to 0, minimize over x. Say f of x is x square plus lambda maybe 3x, right? Okay, so if you now minimize over x, what you will do is this is a simple unconstrained optimization problem, right? So you will set the derivative to 0. So this will be like 2x. So what will this be? Let's just solve this. So it will be 2x plus 3 lambda is equal to 0. Okay, this is like a convex parabola, right? So it will have a minimum. Where will the minimum occur? It will occur at x equal to
minus 3 lambda by 2.
minus 3 lambda by 2. So what you do now is you go and substitute this back there. So this becomes max. This whole problem becomes max lambda greater than or equal to 0. 9 lambda square by 4, right? So 9 lambda square by 4 plus that is what 3 lambda minus 9 lambda square by 2, is it?
Yes, sir.
Okay, minus 9 lambda square by 2. So this becomes what? Negative 9 lambda square by no, what does it become? Minus So it becomes some function of lambda, if you can see that, right? This should be what? 9 minus 18 minus 9 lambda square by 4, correct?
Yes, sir.
Okay, so therefore, this is what is called d of lambda. So in this case, d of lambda is minus 9 lambda square by 4, which is the same as minimize. This is what is d of lambda, right? It's the same thing, but this is the process you have to follow to get d of lambda. It's clear now?
So I think basically this is as Sir said. I mean, Professor said in this thing that we are simplifying a complex problem by taking its duality, which is making it easier for us, as you have very nicely illustrated, that it is making us easier to solve it.
Correct. Yeah. Yeah.
So
Yeah.
that's what Sir mentioned in the video, right?
Right.
When we have a complex, we use the duality to make it simple, because you down very beautifully illustrated how a complex problem can be simplified by this way.
Right. Right. That is right. Yeah. Okay. So that is what we call the dual objective. So okay. Yeah. Okay. So we'll solve some examples. So I have deleted this, but there will be some examples where I do the same thing. So we'll still be
That
there.
will be very helpful, because this, once you put the example, it become very clear.
Right. Right. Yeah. So we will quickly. So there are like some 3-4 examples we'll do. So I'll just quickly go through this sufficient condition and we'll go there. Okay. Okay. So that is the KKT condition, the dual objective. So yeah. Now, so I just want to very quickly, right? So this is important to understand why this is true. Okay. And then we'll move on to necessary conditions, which is very similar to this, and then we'll see examples. Okay. So what is the proof of this? Okay, x star and lambda star satisfy the KKT condition. So that's where we start. So the proof is interesting because it brings together whatever we have been studying regarding convex functions and all that. Okay, so the first observation is that the Lagrangian function, right? What is Lagrangian function? L of x comma lambda is f of x plus lambda g of x. Okay, is a dash function. Do you see what kind of a function this is? Whenever lambda is greater than is equal to 0, what kind of a function is this? So f of x is convex, g of x is convex.
Convex function.
It is a convex function. Okay, so this is actually a very nice result, because a sum of convex functions is a convex function, right? So we have already seen that. So this is because a sum of two convex functions is another convex function. Okay, we have seen this. We have, in fact, I have uploaded the document where I have actually supplied you the proofs. So we think we proved it right at the beginning. Okay, so if f is convex, then any positive multiple of f is convex, and in fact, you can also add 0. Doesn't matter. Okay, so we have used this property, and we have used second property. If f and g are two convex functions, then their sum is convex. Okay, so we have used these two to show that the Lagrangian is a convex function. Okay, in fact, what we are concerned with is L of x mainly, right? Okay, is this clear to everyone that this is a convex function? Okay, hope that is clear. So now what we have to show mainly is this part, right? That it is optimum. It is an optimum for f and d, and they occur at x star and lambda star, right? So now we start with. D of lambda star, okay, and see what that gives us. So what is d of lambda star? Min over x f of x plus lambda star g of x. Is that correct?
Yes, sir.
Okay, so now this is minimum of the Lagrangian, right? So you're taking this whole thing is the minimum of the Lagrangian. So this is actually going to be less than or equal to what? Yes. What is this going to be less than or equal to?
L of x.
It's going to be less than or equal to L of x, right? So it's going to be less than or equal to f of x plus lambda g of x, lambda star g of x. Okay.
Yes, sir.
Okay. Now, since this is true, this is also true for this. In fact, true for any x star, right? So this is also true for f of x star plus for x star particularly, right? So now, what can you say about lambda star into g of x star?
0.
That is 0, right? From complementary slackness, notice that we started off with satisfying the KKT conditions, right? So this is 0. So I'm left with this equal to f of x star, sorry, f of x star. Okay. So far, we have not really shown anything extra, but there is one other change that we can make here. For a convex function, okay, if x star is a minimum, then what can you say about the gradient of the function at that point? If a function is convex, what can you say?
0.
Sir, how you wrote that that d lambda star equal to f x star? Wouldn't it be less than or equal to f x star?
Which
The
step?
third line, yes, yes, the third line.
No, this is equal. This is because of complementary slackness condition, right? This is 0. Lambda star into g of x star is 0.
Okay, then.
Yeah, then this is equal, right? So if this vanishes, this is equal. This is just f of x star itself, right? I can replace the whole thing with f of x star.
Okay.
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 So okay, so for a convex function, if x star is a minimum, then what can you say about the gradient? It's 0, right? So now what happens is we know that, in fact, this is x star is a minimum. In fact, I will put it this way. If gradient is 0, okay, and is the gradient of the Lagrangian 0 at this point? It is, right? So it is 0 because of the first KKT conditions. Okay, so therefore, x star is the minimum of, if you plug in x star here, it is not just less than or equal to, it is actually equal to. Okay, so if you are, I probably didn't explain this very well. So when I upload the notes, I will add little more explanation. So what we will do is, if you didn't understand it completely, it's okay. What I want you to see is finally we arrive at d of lambda star equal to f of x star, okay, which is what we have to show. So when d of lambda star equal to f of x star, something happens. We say that this holds. What holds?
Strong duality.
Strong duality holds. Okay, so this is, recall that the dual is always less than or equal to the primal. Okay, and when you have a convex optimization problem, if you have x star and lambda star satisfying the KKT conditions, then they are the optimal values for the primal and the dual, and strong duality holds. Okay, so I have not given you a proper proof. I have given you only small overview of the proof. There are some holes to be filled in, which I will fill in when I upload the notes. Okay. So this is what is called a sufficient condition. So we have necessary condition also. So this is covered in the lectures mainly. What are the necessary conditions? If X star is a primal, so this is also a theorem. So let's put it in a box. So if X star is the primal optimal solution and lambda star is the dual optimal solution, then provided some regularity, this is not important now. The prof also doesn't mention it, but for those who are interested, let me know. I will point you to the right resources. Okay, X star and lambda star satisfy the KKT conditions. Okay, so that is what we call a necessary condition. Now, I know this is kind of very vague and not quite clear. So what we will do is we will look at these three examples, and then maybe we'll get back to what we have stated here, and things might be slightly better then. Okay, is that fine? Okay, so we'll start with these examples, and then hopefully things will be better. Okay, so this is we'll do the whole thing here. We'll look at the primal problem. We'll also look at the dual problem, and we'll try to solve this. Okay, so each of them. So first of all, is it a convex optimization problem? That's the first question to ask. So is it convex or not?
Yes, sir, because both the functions are convex.
Yeah, both are convex. So it is convex.
Yeah.
Okay, so let's first name these functions. So x square plus 1, this is convex, and g of x equal to x square minus 6x plus 8. This is also convex. Okay, so since f and g are convex, this is a convex optimization problem. Okay, so that is done. Now we can go and look at the primal problem. So the primal we already know, right? So primal is whatever is given to us is already in primal form. So let's go to the dual problem. So tell me what the dual problem will be.
Maximize over lambda greater than equal to 0.
Okay,
Minimize over x. F of x plus lambda g of x.
yeah. So if you plug in f of x, it's x square plus 1 plus lambda into x square minus 6x plus 8. Okay, so is everyone clear how we got the dual problem? Okay, so this is how we got the dual problem. Now we will spend some time in the dual problem because that's the one which is slightly hard here. So let's take step 1, right? We solve the step 1 is solve the inner optimization problem. Okay, so that will be step 1. So how will you solve the inner optimization problem?
Take derivative with respect to x.
Take derivative. So can you tell me what the derivative will be of this function?
2x into 1 plus lambda minus 6 lambda.
2x into
1 plus lambda.
1 plus lambda, correct? Okay.
Minus 6 lambda.
Minus 6 lambda. Okay, this is the derivative, and we set it to 0. Is everyone clear with this step? What has happened? We have taken the derivative of this with respect to x because we are minimizing, right? It's unconstrained. So therefore, we can take the derivative and set it to 0. What do we end up with? We end up
X equal to 3 lambda by 1 plus lambda.
3 lambda by 1 plus lambda. Okay. So therefore, we can know the dual objective function we can formulate, right? So the dual objective function is given by d of lambda is equal to, you have to plug in the whole thing. So this is like x square, right? So this is 9 lambda square by 1 plus lambda whole square plus 1 plus lambda into so once again 9 lambda square by 1 plus lambda whole square minus 6 18 lambda, right, by 1 plus lambda plus 8. Okay, so this is what you end up with. By any chance, has anybody simplified this? Let me see if I have. I think I have the simplified version with me.
Sir, we can simplify this pretty easily. Oh no, we can't.
Yeah, so I have the simplified version with me. So on simplification, I think this is seems to be correct. We get d of lambda to be 1 by 1 plus lambda square into minus lambda cube plus 8 lambda square plus 10 lambda plus 1. Okay, I think that is correct. So this is what you have. Okay, this is upon simplification, this is what you get. Okay, now the question is, how do you solve this? How do you solve for the primal optimum? Sorry, dual optimum.
We should
You have to-
maximize our lambda, so take derivative.
Yeah, you should maximize your lambda greater than or equal to 0. So one way is to take derivative and see if you have the maximum for some positive lambda. We can do that, right? So that is possible. But then this is kind of bit complex. What we'll do is we'll just for the time being we'll just plot this. Okay, so to save some time, now what is this? This is like this is what we have, and I have to change everything to x here. And then I can plot. So by okay, so this is how the dual function looks like. The dual function looks like this. So notice that the dual is always convex, always concave, as mentioned in the lectures. Okay, and you can see that it clearly has a maximum at what point? If you eyeball, what do you see?
2, 5.
It's at 2, right? We get this is the dual function. So dual function turns out to be d of lambda is this one. So d of lambda is a function of lambda. So you put lambda here. Okay, and the maximum occurs at, you eyeball, you can see that occurs at 2. Okay, so this is where the maximum occurs. Now, therefore, we conclude that lambda star equal to 2 is the dual optimum, and d of lambda star, right? So the value of the objective function, dual objective at the optimum is what? You have to plug in this lambda star. And if you do that, I think you end up with, can someone do that for me, please? This, if you plug in lambda star equal to 2, what do you get?
5.
Get 5, is it? Okay, so d of lambda star we get to be 5. Okay, so this is what we have done so far. So we have
Actually, you can see it from the graph itself.
oh, sorry, correct. Yeah, that's right. Yeah, you can see it from the graph. Yeah, it is 5. Okay, so this is the dual problem. Okay, we have solved the dual. Now solve the maybe steps are kind of clear here. So this is the dual problem. Fortunately, in this case, the primal problem is easier in this particular scenario. It's easy to visualize. So first but in general, it may not always be the case. Okay, first let us look at the constraint. So what is the constraint telling us? X square minus 6x plus 8 is less than or equal to 0, right? Now, can you factorize the left hand side?
X minus 4, X minus 2.
X minus 4 into X minus 2 is less than or equal to 0. Okay, this implies X has to be in what range? When is this negative?
From 2 to 4, it's negative, otherwise it's positive. At 2 and 4, it cuts the axis.
Correct. Right? So 2 to 4, right? Those who are aware of this wavy curve, so I don't know if we introduced wavy curve method in Max 1, I don't remember, but there is one nice method where you can, yeah, even otherwise this is not hard. So if you're not able to visualize that very quickly, this is what? X minus 2 into X minus 4, right? This is the constraint. So this is, I'm just plotting the constraint. So where is the constraint negative is what you have to see. Okay, the constraint is negative at in the interval 2 to 4. Okay, so that's the idea. So your feasible set, therefore, the set of feasible points, if someone asks you what are the feasible points, you have to give this answer. The set of feasible points for the primal problem is the interval 2, 4. Okay, so this is the any point which is optimum, which is primal feasible, has to lie in this interval 2, 4. Okay. Now, if you look at it, so if you plot this, in fact, things are very simple. So the objective is x square plus 1. So let's make the constraint in this color. Let's plot the objective function, which is y in terms of x square plus 1. Let's make the objective black. Okay, so objective is black. And we specify the range for the constraint. We are only interested in less than or equal to, right? So this is the region. So in fact, you should not plot a curve. It's better to plot 0. Okay, so this is like that's the constraint region, right? So let's make it very thick so that it's visible and it's red color. So this is the constraint, and this also is active only in 2 to 4. Okay, let's. So yeah, unfortunately that is kind of being clipped off, but it's fine. Okay, so you see that x square plus 1 is anyway increasing. So the minimum has to be at, where is the minimum going to be?
X equal to 2.
X equal to 2, right? So x equal to 2 is going to have the minimum, and do you see what the value of the objective function is at x equal to 2?
5.
5, right? So notice that I will not add that there. So this is f of x equal to x square plus 1. This is f. Okay. So notice that f is increasing here, increasing in the interval 2 to 4, the feasible interval. Therefore, the minimum is attained at the leftmost point of the interval, namely.
So this is strong duality, right?
Yeah, this is strong duality, exactly. That's what I am coming to. So this x star equal to 2, the value of the objective is the primal objective is f of x star, which is equal to 5. And notice that d of lambda star equal to 5. Okay, so we see that f of x star equal to d of lambda star, both equal to 5. Okay, which confirms strong duality in the case of, which confirms strong duality since the problem is convex. Okay, which is what it had to be true, but we have just confirmed it manually. Okay, so that is, all this is fine. Okay, all this is to show you what is happening behind the screens, but we could have done all of this without having to explicitly solve any of this. That's where the KKT conditions come in. Okay, so once this background has been provided, let us now see how KKT conditions make all of this very easy. Okay, so that's the goal. Okay, so now I'll restate the problem. Otherwise, I'll have to keep going back there. So this is the problem. So this is the problem. Okay. So we are going to apply KKT conditions one at a time. So the first condition is stationarity of the Lagrangian, right? So let's define the Lagrangian first. Define the Lagrangian, that is L of x is x square plus 1 plus lambda x square minus 6x plus 8, right? So the first thing is the stationarity of the Lagrangian, right? So if you differentiate with respect to x and set it to 0, what do you get? So same thing, right? So this we already did. So it's 2x. So 2x into 1 plus lambda
minus 6.
yeah, minus 6 lambda is 0, right? That's just one equation which comes from the stationarity of the Lagrangian. And now we start doing the rest, right? So primal feasibility. What does this give us? We'll do all of this for some x. Yeah, so tell me.
X square minus 6x plus 8 is less than equal to 0.
Correct, yeah. So x star square, again, that will be pain. So let me just keep it as x and lambda itself. So x square minus 6x plus 8 less than or equal to 0, which implies x lies in 2 comma 4 as we had found out, right? So this is primal feasibility. Dual feasibility will tell us that
Lambda greater than equal to 0.
lambda greater than or equal to 0. Okay, and finally, what is remaining?
Complementary slackness.
Complementary slackness tells us that tells us what?
Lambda into g of x should be 0.
Yeah, lambda into x square minus 6x plus 8. I'll just 6x plus 8. I'll rewrite it as x minus 2 into x minus 4. Okay. So this implies, so these are the 4 things that KKT gives us. Okay, so KKT is giving us these 4 packets of information. The most useful seems to be the third part. Okay, the complementary slackness in this case. So this gives us what? What are the 3 possibilities? Lambda is equal to 0.
So with these 3 possibilities, we can just calculate the minimum, right? When x is equal to 4 and x is equal to 2, whichever is minimum will give us the point, right?
Yeah, we have to be a bit careful. So in this case, we will achieve it. I'll show you an example, like last example, where it might be hard. So we'll come to that, right? But in this case, yes, you are right. So there will be one minimum, which this will lead us to the minimum. Okay. So there are 3 possibilities: lambda equal to 0, x equal to 2, x equal to 4. Now we have to start eliminating or seeing which one works. So if lambda is equal to 0, what happens? Can lambda be 0? So see, the 4 conditions should not be contradictory. Okay, so if lambda is 0, this is satisfied. This is not affected if lambda is equal to 0. Is the stationarity of the Lagrangian affected when lambda is 0?
No.
We'll get x equal to 0, which is not in the range.
Yeah, so that is affected, right? So that is what we have to check. Now, 3 cases, right? So case 1, lambda equal to 0. 2, 3 are unaffected. Okay, if lambda equal to 0, then 1 becomes what? If you plug in lambda, so 2x equal to x becomes 0, right?
Yes.
X equal to 0, and this is not possible, right? Because x has to belong to 4, right? And this is not. So lambda is ruled out. Lambda equal to 0 is ruled out. So case 2, x equal to 2, which we know in hindsight, we know it's the correct solution, but we'll check. So x equal to 2, complementary slackness is anyway satisfied. Dual feasibility is not affected. Primal feasibility is satisfied. And if x equal to 2, what does lambda become?
Lambda equal to 2.
Lambda also becomes 2. Okay. So, and since lambda is anyway equal to 2, greater than or equal to 0, it does not affect. You have to go back and check that part, right? So it doesn't affect the dual feasibility. That's fine, right? So this works. So this is, therefore what we can say is, we can say for sure that x equal to 2, lambda equal to 0 are the primal and the dual optimum but just for completeness sake, let's see what x equal to 4 has in store for us, right? So x equal to 4, this is fine, this is fine, this is fine. What happens here if x equal to 4?
Lambda becomes negative.
Lambda becomes negative, right? So if x equal to 4 implies lambda less than 0, which contradicts dual feasibility, right? So lambda should be non-negative. Therefore, what we have found is, therefore, we have x star equal to 2 and lambda star equal to 2 are the primal and dual optimum, right? So this is true because of what we call sufficient and necessary conditions. These were the theorems that we discussed before. They guarantee that these are the optimum values. Okay, so without, even if one of them goes out, you can't like be convinced that this is the optimum because of these two theorems, which seem more or less very similar to each other, but in reality they are actually slightly different. Okay, so that keep that in the back of your mind, even if it's not very clear what they mean. But you have to kind of understand that those theorems are what are guaranteeing this final conclusion. Okay, is this example clear what we have done so far? The dual, primal, the different conditions. Okay, I hope that was somewhat clear. Okay, we'll do one more example, and this might make things more clear now. Okay. So once again, we can start. Okay, so let's start with the primal problem this time. First, we'll finish that. Or let's say we'll start with KKT, right? So that's in the exam. If something like this is there, you'll start directly with the KKT, right? So that's what we want to show. We'll start with the first condition, the stationarity of the Lagrangian. Now, what will stationarity of the Lagrangian give us? How many equations will it give us?
2.
So what will the first equation be?
X equal to 0.
Okay, what about the constraint?
X plus 1.
Okay, lambda. Okay, so let's first write down the Lagrangian, right? So L of x is what? L of x comma lambda is half into x square plus y square. Okay, what could I add? Plus lambda times what?
X minus 1.
X minus 1, or what is the general form of the problem? 1 minus x, right? Because see, remember that the general form of the problem is what? Minimize over x f of x subject to g of x less than or equal to 0, right? You have to be careful about the form. So if you this has to be a less than or equal to if we have to have lambda greater than or equal to 0, right? So that is those two are tied together. So the first thing you have to do is you have to convert everything into constraint less than or equal to 0 form. So therefore, what you'll get is f of x is not a problem. F of x comma y in this case, that is still half x square plus y square. But g of x comma y is, you have to be careful. Okay, this is x minus 1 is greater than or equal to 0, which means 1 minus x is less than or equal to 0. So g of x y is 1 minus x. Okay, did everyone get this point? What we have done?
Yes, sir.
I didn't get. How come? How are you getting g of x is equal to 1 minus x?
That's because you should always have constraint less than or equal to 0 form. That is when you will have lambda being non-negative. Okay, so all your constraints in this course have to be mentioned as constraint less than or equal to 0. constraint function less
Yeah.
than or
So
equal
my
to
constraint here is x is greater than equal to 1, right?
yeah, so which means x minus 1 is greater than or equal to 0. So
Oh, yeah. Now I got it. Now I got it. Okay. Okay.
okay, so that is what you have to do. So once you have done this, then you can proceed. So this will be your Lagrangian function. Okay. So then Lagrangian becomes this. Now you can go ahead. So can you tell me what will be the gradients, the
So
partial
you
derivative?
basically adopt the conditions to do it gx is less than equal to 0. That's
Yeah,
what you try out.
right.
Whatever your conditions are.
Yeah, whatever it is, you have to bring it to this form.
Yeah. Got it.
Okay. So what do we get? X.
X minus lambda.
Okay, x minus lambda is 0, and likewise. Okay, here what
Y
is it?
is 0.
Y is 0, right? There's no lambda in this case, so it is just y equal to, there's only y. So that is stationarity of the Lagrangian. Okay, so next we have primal feasibility. What will that give us?
1 minus x is less than equal to 0.
Yeah, 1 minus x less than or equal to 0, and here it's okay, right? Here we can, it's all right to x greater than or equal to 1 is what you will eventually get. So it's fine to state it this way, but when you are, or maybe it's I'll add two steps. So 1 minus x less than or equal to 0, which implies x greater than or equal to 1. Okay. So next one is dual. That doesn't change. So it's
You're getting stationary Lagrangian x minus lambda is equal to 0 because of strong duality x at the minimum point x is should equal to lambda. That's why.
sorry, can you repeat that?
For stationary Lagrangian, you're getting x minus lambda equal to 0 because at the for strong duality x star is equal to lambda star. That's why.
No, right? So at strong duality, f of x star is d of lambda star, right? It is not
Okay. Yeah.
necessary.
Yeah.
This was a very particular case where the values were same, but not in general.
Okay. 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 Okay.
Okay, so complementary slackness will give us,
Lambda into 1 minus x equal to 0.
okay, so lambda into 1 minus x equal to 0. So once again, we are led by this complementary slackness condition. So we can start looking at cases, right? So the case one, we can have x equal to 1, for instance, and look at what happens, right? X equal to 1 will fine with this, fine with this. Is this fine?
Yes.
This seems to be fine, right? So if x is 1, then in fact this gives us x equal to lambda and y equal to 0, right? So x and lambda both 1, that's fine. So x equal to 1 implies lambda equal to 1. Okay, so that seems to be fine. Let's also look at the other case. So lambda is 0. So if lambda is 0, this is fine, this is fine. This for now seems fine, but if you go back here, you are in trouble. Why are we in trouble?
We'll get x equal to 0, which violates second condition.
Yeah. So if lambda equal to 0 implies x equal to 0, which violates primal feasibility. Okay. Therefore, we can conclude, we are justified in concluding that x star equal to 1. Okay. Unfortunately, here also x and lambda are the same. Anyway, so x star equal to 1 is the primal feasible point, and lambda star equal to 1 is the dual feasible point. F of x star is what? F of x star is going to be, is f of x star going to be? F of x star will be
Half.
half. Okay, f of x star is half, and ideally should be equal to d of lambda star. Let's see. So d of, we have to now compute d of lambda star. So okay, let us see if d of lambda star is indeed half. Okay, that's what you have to do. We'll do that and then we'll close this example. Okay, so where are we? We were looking at right. So let's do that. So okay, so that's the KKT conditions, right? So KKT has given us the optimum. We'll just verify it. So verify the dual optimum. Now, what is the dual? It is min over x half into x square plus f of x plus lambda into
1 minus x.
1 minus x. Okay, so once again we solve this minimization problem. Now remember that we have already done this gradient, setting the gradient to 0, right? So we have done this. So this is what we'll have. So x equal to lambda, y equal to 0, plugging this back into the dual objective, we end up with d of lambda to be lambda square by 2 plus lambda into 1 minus lambda. So it is lambda minus lambda square by 2. Is that correct?
Yes, sir.
Okay. So this is what? This is nothing but lambda into 1 minus lambda by 2. And if you plot this, this will be a concave parabola, right? So once again, if you conclude, we can see that the function is concave. So dual function is always concave. So lambda into lambda minus lambda square by 2, right? So, and the range is, the maximum occurs at 1, okay? And sorry, maximum occurs at 1, and the value is half, which is what we wanted to see, okay? So this is once again d of lambda and versus lambda. Okay, so that's the dual problem. Now we go back to the primal. We can visualize the primal also. So verify the. So this is not too hard to see. If you look at the primal problem, right? This is what geometrically you can see this. This is true. So back to the primal. This is visually what is this? The constraint. What is the constraint here? Can you think? Can you visualize the constraint? What is it telling you?
X should take values greater than or equal to 1.
Correct. So the constraint is like two-dimensional. If you think about two-dimensional plane, what does x greater than or equal to 1 mean? Set of all points x comma y for which x greater than or equal to 1 will mean what? So will mean x in terms of y. So x greater than or equal to 1 is this half space, right? This is like this convex region. This is x greater than or equal to y. So any point in the plane for which x coordinate should be more than 1 or equal to 1. So that's the constraint. Now what is x square plus y square going to look like? It's going to look like a bowl, right? So it's like a bowl centered at the origin. If you can think about it, this is like a sheet of paper and you are placing a bowl on top of it, on top of 0. And the height of the bowl is going to keep increasing as you move away from the origin. Okay, so the height of the bowl will be the minimum in this constrained region. When will it be minimum?
When it just touches the x equal to 1. That
Yeah,
is 1, 1.
Yeah, exactly. When it just touches that x equal to 1, that is when it will be minimum, right? So you can draw the contours of the bowl. So in this case, it's x square plus y square by 2, right? So divided by 2 minus 1 minus 2. So minus 0.5 is the minimum. So this is one constraint. So this is like one contour. We make it black. That becomes. This is the contour where it is minimum. Okay, so I'll draw two more contours where it is one is greater than one where the function's value is bigger. So this is where it is bigger. So this is let's make it black dotted, and I'll draw one where the constraints the function's value is slightly smaller. Okay, so this is again black dotted, and this is maybe 0.25, okay, or 2. So these are the contours of the objective. So this is like there are beads. This is okay. So these are the contours of the objective, and this maybe the particular contour where it's minimum. I'll highlight it. I'll maybe give it a red color. Okay. So this is where the contour just touches the constraint. Okay, and that is your minimum. That is your X star. So X star is 1, 0. Sorry, X star, Y star. Okay, the point where the bowl just touches the region X greater than or equal to 1. Okay, so just to draw, make sure that this is clear. This is what we are talking about. Okay, is this clear to everyone? Okay, so this is the idea. All right, so we look at one more example. It's a slightly complex example because there are multiple inequality constraints, but this also has a very nice geometric interpretation. Let's.
So it is a rhombus kind of, it's a square kind of a structure that is 1, 1, 1 minus 1, minus 1, minus 1, and what is left 1 minus 1.
Right, yeah.
And this is a ellipse with centered at 3.5 means 1.5 and 0.5 with a radius of well, I don't know.
Yeah, so yeah, we'll come back. Yeah, we'll come to the visualization part soon. Okay. So what are we doing here? We'll do the KKT first. Okay, first the Lagrangian. But first the Lagrangian and then so x comma y comma lambda, right? This is what? This is, we just copy this. This is plus. In fact, this has to be yeah, has to be plus lambda 1, okay, into x plus y minus 1. That's the first constraint, plus lambda 2 into x minus y minus 1 plus lambda 3 into minus x plus y minus 1 plus lambda 4 into minus x minus y minus 1. Okay, so this is the Lagrangian. Is this clear?
Yes, sir.
Okay, so now the first condition, the stationarity of the Lagrangian. Remember, you have to do it for x and y here, right? Once again, you have to you'll get two equations. What are they?
Two
Yeah,
into minus
yeah.
3 by 2
2 into x minus 3 by 2, okay,
plus lambda 1 plus lambda 2
plus lambda 1 plus lambda 2,
minus lambda 3 minus lambda 4 equal to 0.
okay. What about the next one?
2 into y minus half
Okay, 2 into y minus half,
plus lambda 1 minus lambda 2
okay,
plus lambda 3 minus lambda 4.
Okay, this is 0. Okay, so that is one condition. Now, next we have is primal feasibility. So, stationarity of the Lagrangian primal feasibility. Primal feasibility you just copy. Okay, so it's nothing extra. And dual feasibility, how many are there? No,
4.
4 are there. Okay, so we just call this lambda 1 greater than or equal to 0, lambda 2 greater than or equal to 0. Any lambda I is greater than or equal to 0, right? So, and then lambda 4 greater than or equal to 0. Okay, so finally you have, once again, how many conditions for complementary slackness?
4.
4 again. Okay, so what we'll do is we'll just copy this, paste it here, and we'll bring all of this to one side, and then we'll multiply by their corresponding lambdas. Okay, so this is lambda 1. So this will be lambda 2 into x minus y minus 1 equal to 0, and this will be lambda 3 into minus 1 equal to 0, and lambda 4 into. Okay, so that is complementary slackness. Now we are not going to solve this. Okay, so it's not so easy to. It's not. I won't say it's hard. It's just that it's not so straightforward. Okay, so what I'll show you is I'll quickly show you the. Maybe you can try to solve this offline and let me know what you get. But maybe quickly, what do you think will be a strategy to solve this? What could be done? Can try eliminating some of these values, but even then it's going to be quite hard. Okay, so why did I give you this example? Is just to give you a sense of what happens when there are multiple constraints. Okay, that is the only reason I gave you this example. So if there are multiple constraints, what you have to keep in mind is you need as many KKT multipliers as there are constraints, and you must know how to write down the stationarity, the 4 KKT conditions. You must know to write it down. So you won't be asked to solve this in the exam. It's something as complex as this, you won't be asked to solve. But I just want you to know that this is the procedure to approach a problem which has multiple constraints. Is that clear for everyone?
Yes.
Okay, so visually what is happening is the following. So if you plot these curves, right, these are actually very nice inequalities. So these are of the form what y greater than x minus 1. So in fact it's less than or equal to. Okay, this is one kind of no, what did we have? It's actually where are the constraints? X plus y less than or equal to 1. So y is less than or equal to 1 minus x. So y is less than or equal to 1 minus x. Okay, this will be one region. Similar plot. Y less than or equal to minus 1 minus x. No, not minus 1 minus x. 1 plus x will be another region. Okay, so notice that now you have this common region so far, and you can also do this in terms of y. So 1 plus y. Okay, what am I missing? This is what should this be? In fact, sorry, it's easier for me to draw it freehand rather than give it to you this way, because it's taking, I'm not able to figure out exactly what these inequalities are. So I'll put it this way. You have an axis, and you have +1, -1, +1, -1 on the 4 sides. So you will have shape like this. Okay, so this will be 1 and 1. Yeah. Okay. And then parallel to this. Okay. And you have 1. And then parallel to this, right? So square with points resting on 1, 0, minus 1, 0. And what else? 0, 1 and 0, 1 and
0 minus 1.
0 minus 1. Okay. So this the shaded region inside the square. Okay. So that is going to be, in fact, maybe I can do a better job of drawing this. Should have done it anyway. So this, let me, sorry for the delay. So what I'll do is I will delete this and then insert the square fellow here. That's better. Okay. So that is so that I can shade this constrained region. So that is your constrained region. And so the 4 constraints together will look like this. Okay. This region inside is what you'll have. And your this is the equation of what?
Contours of circle.
Yeah, it's a circle. Okay. So if you draw the contours, you'll get circles. So these circles are centered at 3 by 2 comma half. Okay. So that's like 3 by 2 is somewhere here, correct? 1.5 comma half. So it's somewhere here. So you can think of, so it's 3 by 2 comma half. So it's like the smaller the circle, bigger the functions, smaller the function's value. So you're minimizing. So there will be a point. So I'm not drawing it correctly, but if you actually draw it correctly, one of the contours will exactly hit 1 comma 0. Okay, that's the first time when it will hit the constrained region. And that point will correspond to the minimum, okay, of the primal problem. So at that point, 2 of these constraints will remain active. The other 2, for the other 2, lambda will be 0. Okay, this is all extra info. So you don't need to worry too much about it if you don't understand this. But I strongly urge you to visualize some of these contours and see what is happening. Okay, you can use the same tool and try to draw these graphs. And you should be getting something like this. Okay, is this example clear? I hope the motivation.
What is the tool you are using and how to use it? Means, I don't know.
So this is a mathchart.io, mathcha.io. If you go there, you should be able to do. So if you just click on plot, you will be able to plot, and then you can figure out. So it's not too hard to figure out how to do this. Okay.
So what is the solution here, sir?
What do you
what?
mean? Mathcha, right?
Yeah.
The spelling once.
mathcha.io. cha.io. So you should be able to do it.
No, sir. I'm asking, sir, what is the solution of this problem, sir?
Solution, yeah. So when I upload it, I will share it with you. So you will notice that 2 of the lambdas will be 0. The lambda corresponding to this constraint and this constraint will be 0. And the other 2 will be non-zero. They are what are called as active constraints. 1 comma 0 will correspond to the primal optimum. And if you substitute 1 comma 0 here, you will get whatever, right? So that will be the primal objective. See,
So you were saying that we can work out the solution and send it to you. So how do we send it to you? Through email?
No. So if you can post it on Discourse, if you have managed to solve this problem step by step.
Can you give me please the link to the Discourse? I'm sorry.
Yeah, Discourse. You have this is Discourse, right? So you have to look at our particular course, MLF course forum.
Okay. And the recording of this, and you will be uploading the this thing, what do you call the notes in the coursefed where they give the this thing, right? That Google Drive, right, where the course where this thing is.
Yeah, supplementary content, you will be able to find this.
Okay, yeah, got it.
Okay, so the caution. So why do I have a problem that says caution? You will understand. So that is what we'll do next. Now, by just looking at this problem, what is the solution to this? So is this first of all convex optimization problem? Yes or no?
No,
Why? Why do you feel that way?
because e power x is convex, but negative of it is concave.
Correct, but that negative of e power x will be minus e power x, right? So this is e power minus x,
Okay.
right? So this is also convex. So yes, because you look at e power x, so e power minus x, then what you do is you take f double prime of x, right? So of x is nothing but e power minus x is minus e power minus x, f prime, f double prime is e power minus x again, correct? Okay, and this is always positive. So this implies f is convex, right? So the second derivative should be non-negative. That is the test for convexity. So f is convex because of this reason. G is anyway just x, so that is convex, okay, or minus x. So first define f of x. So f of x is e power minus x, and g of x is minus x. Why is g of x minus x? Why should it be? Why shouldn't it be just x?
We have to convert it in the form of less than equals to
Correct,
0.
yeah. It's again the less than or equal to kicks in. So right. So f and g are convex. So this is a this is a
But
convex.
this minus x is both convex and concave.
Yeah. Minus x is both convex and concave. Yeah.
Okay.
Okay. So this is a convex optimization problem. Therefore, let's see what the KKT gives us. So KKT will be very funny for this. Okay. So stationary.
Since g of x should always be less than equal to 0, therefore you only if x is negative, it will be always be less than 0 because x is always positive, right?
So we'll come to you are right. So we'll come to the understanding of it soon. But before that, let's just quickly do the KKT. Okay. So KKT will tell us, in fact, the Lagrangian is what? So Lagrangian is in this case e power minus x plus lambda minus lambda x, correct?
Yes.
Okay. So the stationarity of the Lagrangian will tell us that e power minus x minus lambda equal to 0, correct? And primal feasibility is telling us x greater than or equal to 0.
So
Dual
the
feasibility
first one should be
Minus,
minus.
Yes, minus e to the power.
minus e power minus x minus lambda, correct?
Yes.
Okay. So dual feasibility is telling us lambda greater than or equal to 0, and complementary slackness is going to tell us that lambda into x is 0, correct?
Yes.
Okay, so we have a very funny set of KKT conditions. So this implies that lambda is equal to minus e power minus x. From this, what can we say about lambda? It is
Negative.
negative, right? It's in fact strictly negative because e power x can never be 0, and this is minus e power x is always, sorry, this is e power minus x, correct? E power minus x or e power x, whatever you consider, is always e power something is always positive. Therefore, lambda is negative, and there's a direct contradiction. Okay, so lambda less than 0, lambda greater than or equal to 0. So there's, in fact, this clearly you are not able to control anything, right? So you're not able to find any solution here. So, and if you go back to the original problem, this should have been obvious by just looking at the original problem, right? So this is, does e power minus x have a minimum when x is greater than or equal to 0? It doesn't, right? So e power minus x is what? So visually, what is e power minus x? It's just this. Specifically, if you consider the range infinity, I'm just putting in some specific value here. So the function is just keeping on decreasing. It never, whatever value, small value you find, there will be a smaller value when you step towards the right. Okay. So why is this? Why have I mentioned that term caution here? Is because if you look at the theorems, the two theorems that we were looking at, right? So what did they say? What they are saying is, if you find x star and lambda star satisfying KKT, then this is a minimum. And the other theorem is telling you that if x star is a minimum and lambda star is a dual optimum, then they satisfy the KKT conditions. Okay. They don't tell you that there is always that there always exists one such x star and lambda star. Okay, so what I mean by that is, where are we? So what I mean to say is, KKT conditions do not guarantee the existence of an optimum for every convex optimization problem. Okay, so this is important to understand. So there may be convex optimization problems which do not have any solution, like this example, right? So this does not have any minimum. So this is, if you try to solve this problem, you will realize that there is no minimum. Okay.
So basically, you're saying that it meets the KKT conditions, but still it doesn't have a minimum.
No. So the KKT conditions are also returning no value, right?
Yeah, I mean, when you so basically you're saying that if you have two convex functions, still you may not have a minimum,
yeah,
right?
so exactly. Yeah. So not all convex optimization problems need to have a minimum, is what I'm trying to say here. If they have a minimum, right? So if a convex optimization, so there are 2 points. Okay, in fact 3 points. So KKT conditions do not guarantee that every convex optimization problem has a minimum. Okay, so there may be convex optimization problems which do not have any solution, but if a convex optimization problem has a minimum, then KKT condition will help us find the minimum. Okay, this is guaranteed. That is what a theorem guarantees. If you have a minimum, then KKT conditions is all you need to locate that minimum. Okay, of course, assuming. So all this is with a warning, assuming you can solve the equations generated by the conditions in closed form, right? So, or rather, assuming that you can solve the equations generated by the conditions. Okay, this you have to be careful. It is not necessary that the equations that you end up with are always, in a nice closed form. Do you all understand what I mean by closed form?
Basically, it leads to finding a minimum where fx star is equal to dx star, right?
Yeah, you should be able to, find out the minimum in terms of usual math operations like, taking square root, adding, subtracting, division, squaring, exponentiation, right? But if the equations are too complex to solve, then you have to rely on numerical solutions. Okay, meaning use a computer and try to iterate and do things like that. So, did I confuse you a lot in this part? Is this clear?
No, I guess you're basically trying to say that you have a convex function, and then you have a constraint which is also a convex function. Now your KKT, once if it meets the KKT conditions, that means you will have a minimum. If it doesn't meet, you won't have. I mean, that is true for any mathematical issue, right? That's why mathematics is so interesting.
Right, but this is, you are right, but this is like a slightly more complete situation. So the KKT conditions are in some sense both necessary and sufficient. So it works both ways is what I'm trying to say. It is not the case for every optimization problem. So there are certain situations where things work only in one direction and not in the other direction. Okay. Yeah, but it's okay. So if I didn't make sense here, I hope that shouldn't be too much of a problem. So main thing that I want you to take away is the last example in this case is convex optimization problems needn't have a solution. Okay. But if they have a solution, KKT conditions will be satisfied at that particular point. Okay. If you maybe that I'll stop there.
So there is other way of thinking about it. So you have a convex function. Then when you do a duality, it basically transforms into a concave one also. That's the dual problem, right?
Right.
Now the convex and the concave may not meet. In that case, you do not have a solution.
Concave will not meet what?
The convex, you have a convex function, okay, and then you the duality, basically when you say duality, it is expressing in a concave manner where the dual function, right?
Yeah.
So what you're basically trying to say is that when you convert a problem into a convex problem into a concave one, they may not meet, right? They may not meet at a point.
Which two are meeting?
See, when you have a convex function, right?
Yeah.
Okay, and you have a convex constraint. When you are converting into a dual function, I believe what professor had said is that it basically converts into a convex, this thing into a concave one, right?
Correct. Yeah, it's a concave. It becomes concave. Yeah.
Concave, right? So basically, if you look at, okay, then all right, I'll not go in further because it might confuse people.
Right. Yeah. So when you say they're not meeting, I see these are two different optimization problems, right? So there are two different regions you are looking at. One is in Rn, another one is in some other space, right? So I'm not sure if you can necessarily talk about both of them sharing the same common region. But yeah, you are right in saying that this is, yeah, I kind of get what you're saying by they don't meet, but yeah, I also think we should probably stop this particular portion here. Yeah, so any questions so far in what we have discussed in the 4 examples that we have discussed? Are there any other questions? Any more questions? Anyone? Okay, so in that case, I think we are largely done. So there are few more points that I have, few more questions that I had. These are like just in the activity. So do we want to do them or shall we? What do you say? Do you want to do any of these? These are more along the lines of which of these functions are convex.
Yeah, I think we still have 20 minutes around. We can go through it. If people are interested, they can stay back, right?
Yeah, I don't mind doing it. So yeah, I'll just 3 questions anyway, right? So we'll start with this. So this is there in the activity, but it's just MCQ, right? So we really don't know why they are not convex. So clearly these 3 are not convex. Okay, need not necessarily be convex. You have to give me an example, a counter example for each of these cases. So let's take f of x into g of x. So f and g are convex. So can you give me examples of f and g for which f into g will not be convex?
E power x and minus x.
Okay, a power x, e power x or a power x?
E power x.
Okay, so f of x is e power x. Okay, this is convex, and
G of x is minus x.
okay, that is fair enough, right? So
Yeah, e power minus x, I think. Did you say e power x and e power minus x?
I said e power x.
E power x and just minus x, is it?
Yes.
Okay. So let's first plot this. You'll end up with x e power minus x e power x, right? So it is clearly not convex. Is it concave, by the way?
Half concave.
Half concave, right? Yeah, by the way, why is it not having anything on the left hand side? The left branch of the function is it missing, or are we?
No, we are finding a negative of e to the power x, so it has to be either this side or that side. That means one
No,
side.
you're asking e to x.
So for x equal to -1, what will this be? This will be minus e power -1, right? So it should show up. Why is it not showing up? So this kind of doesn't see. E power x is there. Okay, x e power x. We should x e power x suddenly. Should x e power x suddenly disappear? Once again, so okay, this is malfunctioning. Okay, because if you look at Desmos, this is not the case. I think there's something wrong with that. That tool is not working. Yeah, this is minus x e power x, right? So
there may be a bug, right, on the program.
Yeah, that should be a bug. It's unfortunate, but yeah. Anyway, I'll copy this and move it there.
This is not a
So can we take the example of e to the power x, fx equal to e to the power x, and g of x equal to e to the power of minus x?
But if you multiply the two, you will get 1, right?
Yeah.
1 is convex, right? It's convex
Okay.
and concave. So yeah, so we have f of x, h of x equal to h equal to f into g, given by h of x equal to minus x e power x. So visually it is clearly not convex, but we should also justify it algebraically, right? So what do we have to do for algebraic justification?
Second derivative.
Yeah, we'll find the second derivative of
It should be positive. Second derivative should be positive.
Yeah, so let's first take the first derivative. Now h prime of x is what?
Minus e power x minus x e power x.
Yeah, minus e power x minus x e power x. Okay, so which means h double prime is what we get?
minus e to power x minus e to power x.
The same thing, same above thing repeated again, right?
Yes.
But then with a minus sign, correct? Oh, no, not minus sign. It's exactly the same thing. So is this correct? Is minus 2 e power x minus x e power x? Is that correct?
Yes, sir.
Okay. So now, so this is if we kind of pull the e power x out, you end up with 2 plus x. Okay. And what can we say about this?
This is not positive, right? Because e to the power of x is this thing, and you're
No,
multiplying.
x equal to less than -2, it is positive, no?
Yeah, so it is actually concave in the region. Sorry, it's convex in the region.
X less than -2.
Yeah, so it is. You could say if you restrict the set to, if you go back to this, right, and if you look at -2 onwards, okay, if you restrict the function to -infinity to -2, it is indeed convex. But then overall the function is, if you look at you define h as r to r, okay, the function from r to r, then it is not at all convex. In fact, from -2 to -2 to infinity, what can we say? It is
Asymptotic to the axis.
right. No, what I am saying is from -2 to infinity, can we say something about the function?
That it's concave.
I think we can say it's concave, right? So, but anyway, so we have to be careful. So we should say that where the domain of H is R. Okay, so if the domain of H is R, then we see that. So we see that H double prime is, sorry, what is double prime? Second prime D prime. So of X is negative at certain regions of the domain. Hence, H is not convex. Okay, so remember the condition is that H double prime of X should be greater than or equal to 0 at every point in the domain. Only then is the function convex. Okay, so that is a counterexample for this. So what about f of x by g of x? Is there a example you can think of? Where f and g are convex, but f by g is not convex.
Gx is equal to 0, then
it's like no, right? So think of something where. So simplest thing is like the previous example, right? Some negative, if some negative fellow comes in, then that fellow.
Yeah, so basically if you look, f into gx and f by gx are the same. I mean, you are multiplying it by 1 by gx, right?
Sir, it is minus x e to power minus x. It will be work, sir. Minus x e to power fx is e to power minus x. So it will miss when.
Yeah, you're right. So what you're saying is
function,
g of
same
x,
function, sir.
yeah, you're saying g is e power x, right? So then it will be minus x e power minus x. So
Yes,
we
sir.
should end up with a similar result there. So if you have, yeah. So but this looks. This is actually from visually. What can we say? Is this convex or concave, or rather, is it convex? Does it look convex?
It is convex at a certain this thing interval, right?
Yeah. So especially here, it's not convex, right? So for example, from 1 to 3, if you draw a line from, or maybe from here to here, what is happening? So doesn't look like it's going to be convex, right? There is a dome-like region that's jutting out here.
It is
But if we draw epigraph, then it will be above that curve. So why it won't be convex at that region?
no.
The epigraph should be convex, right? So does the epigraph look convex here?
No, sir. From after 3, it is again shape is changing. So there may be chances that some points are out of the curve. 3 and 4, the shape is changing, no, sir. Shape is again
Yeah.
changing.
So correct. Yeah. So here it is convex, but at some point it is indeed changing the. It is becoming more concavish there.
Yes, sir.
Okay. So see, a simpler example would be the following, right? It's a very trivial example, but you can have f of x as x square, and if you want something that becomes concave, what can you put g of x as?
1 by x.
But g should be convex, right? You should have convex g.
Can we simply put it as x?
If you put g as x, f by g will be x again, right? So that is still convex.
Negative of
Negative of? Negative, can we just put it as minus something? Will this work?
yes.
Right, so this will work, right? So this is
Yes.
this is just the constant function. So this
Yes,
is
minus x square. Minus, it is f of g, f divided by gx minus x square.
yeah. So in fact, this will work for even this f into g and f by g. So what about f of x minus g of x? So you should be able to think of a lot of examples here. So if I start with x square again, what can this be?
Minus 2x square.
Minus 2x, okay, but then that will be concave, right? That will make g concave. So g should also be convex. If you want the output to be minus 2x square, what should g be?
3x square or something.
3x square, right? So something like this. So if you have something like this, f minus g will be concave because it will be negative x minus. In fact, you can just have minus. You can just have 2x square. So this will be minus x square. Minus x square is concave, right? So yeah. So that is about examples. Coming up with counter examples, right? So I hope that is clear. So what about this? Is x into log x convex?
No,
Okay, why do you think that way?
because log x is concave
Okay,
and x is both convex and concave.
okay. Therefore,
And x is from 0 to infinity, so it's like multiplying a positive parameter to log x.
okay. So let's plot this and see.
So it will remain concave. I think that's what it is, right?
Yes, sir.
Okay, so what do you? This is x log x, right? So the base doesn't matter, but anyway, so this is maybe I'll draw base c itself just to be safe. Yeah. What do you still stick with your original answer?
It looks convex.
It looks convex, right? So that argument that you made is I won't say it's wrong, but it's I mean it is a bit tricky, right? You have to be careful there. So whenever you are given a function like this, always safe to go by the usual theorem that uses the second derivative, right? So let's start with that. So what will be f prime of x for x log x?
Log x plus 1.
Yeah, so if this is x log x, this is log x plus 1. Okay, and what is f double prime?
So for negative that is not defined, fx is not defined.
Yeah, that's why the domain is 0 to infinity, right? So
Yes, sir.
this is
1 by
1
x.
by
1 by x, right? Which is always greater than 0 for all x in the interval. So this is 0 to infinity, right? So which is therefore what you see is f is in fact convex. F is indeed convex because of the above result that the second derivative is always greater than 0. So see, log x is concave, that is correct. And x is both convex and concave, but we have just shown that f of x into g of x need not, we haven't shown this, but f of x into g of x need not always be convex, right? So see, if two functions are convex and if you multiply them, they don't necessarily retain convexity, right? So likewise, if two are concave and if you multiply them, do they retain their concavity? We don't know, right? So that's why that argument is slightly dangerous, right? So always go by the second derivative. See
So
if
that is a safe method to check.
yeah, that is
for sure.
yeah. Okay, so that is so final problem. You have max of x1 to xn. So this is actually kind of norm that we haven't studied so far, but this is what is called the infinity norm. Okay, but yeah, if you put absolute value, it is the infinity norm, but it's closely related to what is called the infinity norm. But anyway, so if you take the maximum, so what is this function? So for example, if n equal to 3, the function will look like this. So f of x is max of x1, x2, x3, and sample function evaluation say 1 minus 2, 3 is equal to 3, right? And f of 4 minus 5, 1 is again, okay, let's maybe make it 4. This is 4. Okay, so that's what the function is. So it just returns the maximum of the n coordinates. So is this function convex? What do you say?
That I think no, it should not be convex.
Okay, why?
Because it at every point it will take maximum, so it will be like concave type kind of.
Yeah.
Sir, if we think about
Yeah, if you take a maximum, it is always going to be a concave or a parallel half plane, which is actually a concave function only. While if you had taken the minimum, then only it could have been a convex one.
Okay.
In 3 points.
Sir, if we work with an example and take like f of 5 comma a, and if a is less than or equal to 5, the value will be 5, and if a is greater than 5, it will keep on increasing, right? So maybe it's concave and convex because those are like lines, linear lines.
Okay. All right.
We can use permutation and combination of these three things and make the equations like x1 less than x2 less than x3, and similarly do the combinations required 8 permutations or some lesser combinations, and thereby plot a general curve and make a statement.
Okay. So does any of your definitions work here? So what is the original definition for a convex function? What is that?
So that if you join any 2 points, it should remain within that particular curve, right? Here it can be random points. So therefore, that first definition will not hold true.
Yeah, but we have to verify, right? So we still have to check. So we'll go back to the original
Am I right on what I said?
We will see, right? So we'll work it out once you. So for a function,
Sir, I have a small doubt. Like, if function is not differentiable, it won't. Does it affect its convexity or not?
so the last two definitions, right? So one which involves the Hessian and or rather the second derivative
Yeah.
and the other test. So they can be applied only when the functions are differentiable. But we saw mod x, right? Mod x is an example of a function which is not differentiable everywhere, still convex. So you can't really comment on the convexity if it is not differentiable. It could still be convex.
Okay.
Right. So therefore this is kind of that situation only, right? It's a tricky situation. So what we have to do is we have to go back to those definitions which do not involve calculating the gradient or the derivative, right? So the first definition is one such definition. So for a function to be convex for any 2 points, right? X1, so x comma y, we have and for any lambda in 0 to 1, right? We need, what do we need? So we need to show that f of
F of
lambda
lambda
x,
times
this is what? This is greater than or equal to or less than or equal to?
less than equals to
Less than or equal to lambda f of x plus.
lambda 1 minus lambda times f of y.
Okay, so now let's take let's take the simple case of x. Let's call x as x1, x2. Let's take y as, of course, it is y1 to yn, but let's simplify this for just 2 coordinates. It should apply for any general case also. Okay, so what are we having on the left hand side? Lambda x, let's try to understand this. Lambda x plus 1 minus lambda y is what? 2. Something comma something. This is lambda x1 plus 1 minus lambda y1, comma lambda x2 plus 1 minus lambda y2. Is that correct?
Yes, sir.
Okay, that is one part of it. Now, so that this part we have computed. Let's compute lambda. So f of x is what?
Maximum of x1, x2.
Maximum of x1, x2. And f of y is likewise? F of y is maximum of
y1, y2.
y1, y2. So, yeah, so this is where it becomes tricky. So,
it's 10 o'clock.
What is f of, so this we know, therefore we can ask the question, what is f of this? F of this is just f of this, right? The whole thing. Correct? This is equality here. So far I'm not doing anything that has to do with inequality. Sorry, this f is outside. This step is clear, right? I'm just applying f on both sides. Okay, so now this is what? F of this big thing is what?
Maximum of those two coordinates.
Yeah, maximum of these two. So lambda x1 plus comma this. Okay. So too many expressions. Like let's try to understand what we have here. So this left hand side, I'll call this LHS. That is this quantity. Okay. The right hand side is what? Right hand side is what?
Lambda times maximum of x1, x2.
Yeah, exactly. Is this plus 1 minus lambda into?
Maximum of y1, y2.
Okay. All right. So this is what you have to. So if you can show that LHS less than or equal to RHS for any lambda in 0 to 1, you are done. Okay. Assuming it is convex, of course, it may not be convex. But the question is LHS less than or equal to RHS for some lambda in 0 to 1? What do you think?
LHS should be less. No?
I think it's for what I have seen, the height of the curve is always less than the height of the line.
Yes.
So that.
Okay. So can you say that this is always less than or equal to this? Now it's hard to visualize here, so you'll have to go by some kind of algebraic argument.
Sir, I have a question here. The question is this: when we are referring to the max of 3 points, the function itself actually is comprising of only 3 points. It's not even a curve. Then what are we seeing as a concave or a convex? First, it has to be a curve. We are thinking there is a curve.
There is, right. So there is some. So if you have 3 points, it's not a curve. It's some hypersurface, right? So you're looking at. It's easier to think of two. So if it is x1 x2, it's some surface in R3, right? You're looking at some surface in R3. X1 x2, max of x1 x2. You have to plot this as x comma y comma z in R3. Yeah, that's what I said, right? So this is a valid function. If you try to go by geometric arguments, it's going to be hard for this, because first of all, visualizing this itself is hard. So what I am suggesting is this part is clear, right? Why we obtained LHS and RHS like this?
Yes, sir.
Okay, now if you want to, of course, you don't know if it is convex or not, but if you want to show that it is convex, it is sufficient to show that LHS less than or equal to RHS. The question is, can you do that? Now I'll tell you that it is convex, and then I'm going to ask you, how do you show that it is convex? Okay, first of all, if you look at the RHS, can you take the lambda inside? Is this permitted operation? Is this a permitted operation?
Yes, sir.
Okay. Why is this permitted? Because lambda is
a constant, so you can always take it inside.
It's a positive value, right? More importantly, lambda in 0 to 1. So if lambda is negative, for example, it's a bit tricky, right? So lambda is anyway between 0 to 1, so you can for sure take it inside. So particularly if lambda equal to 0, anyway it doesn't matter. The result will anyway be 0 if you take it inside or outside. If lambda is some positive quantity, then it doesn't, scaling them doesn't change the maximum, right? So it's fine. So you can take it inside. Now this is like the new RHS. It's the same RHS, but we have modified things a bit. And this is your LHS. Okay, this is what you have now. Now, do you see anything happening here?
You can we just separate out x1 and x2? See, on the LHS you have x1, right? Lambda x1 and lambda x2,
Yeah.
and below you have, so I mean, we can consider x and y separately and see that, okay, if it's maximizing out, even if it is, I mean, this thing, right? We can see it in that fashion.
Correct. That is what you have to argue now.
Am I thinking in the right direction?
Yeah, correct. Yeah, you have to break it down. So you have to show that this is, you can actually break it down into, you can group these two together somehow, and you can group these two together somehow. So you have to argue why is it that you can do that?
Yeah, so in the top, see, LHS, you have max of lambda x1, okay, and then and if you take x and y separately, you have lambda x1 and lambda x2. In the RHS, you have below again lambda x1, lambda x2. So if you just separate it out the coordinates, okay, then if you have maximum, suppose it's lambda x1, okay, you get the maximum in the RHS. So you will similarly get the maximum in the LHS also, if you consider it separate x1. Similarly, if you do it for y1, okay, if it is I mean, if since lambda is within 0 to 1, okay, so in that case also, if you multiply y1 to something below this thing, maximum it will take, the maximum value which it will take will be equal to whatever is on the RHS.
Right. So you have to rigorously establish that.
Yeah, I mean, I gave a very bad explanation, but I think you got the drift.
Yeah, so what we have is we have 4 distinct quantities, right? So you can think of this as A, B, right? Okay, and okay, so can we rearrange the LHS now? What is LHS actually telling us? It is max of
A plus C comma B plus D.
okay, and what is it we have to show? It is less than or equal to
Max of A comma B plus max of C comma D.
okay. So these are all. So this is what we have to show. Now, if you think about it, max of A plus C comma B plus D, right? It can be what? It can either be A plus C or B plus D, right?
Yeah.
Do you agree? So it can be one of these two. So let's say it's A plus C. Okay. Now, what is A less than or equal to? Maximum of, I can replace A by something bigger than A or equal to A. So I can replace A by the maximum of A and B, and I can replace C by the maximum of C and D. Correct? Do you agree this argument?
Yes.
So you can once again you can go the other way and you can say so this is A plus C, B plus D. You can say this is D plus D, and you still can replace this with something bigger than B or equal to B, or you can replace this with something bigger than D or equal to D. Right? So both ways you see that this is satisfied. Okay, and this is true for any ABCD. So for any ABCD, this is true. Okay, so LHS less than or equal to RHS. Therefore, what we have just shown is LHS less than or equal to RHS for any lambda in 0 to 1. And all of this is to show that, goes back to show that F is convex. Okay, because the original definition of convexity is satisfied. Is that fine? Okay, did everyone get this idea why this is convex? Okay, right. So that is all I had. Now, any questions? Anyone? Any other questions? Yeah. So then what we'll do is we'll continue with stop the recording. We'll continue with before you all leave. I just want to tell you that yeah. So I've stopped the recording. So